think we can start now. Is it? Okay. All right. So multiple comparisons. So I'm going to start with discussing a few issues with the current approach to correcting for multiple comparisons in neuroimaging. Then I'm going to motivate a new approach with two toy examples. After that, I'm going to demo with a real data set. It's pretty much typical box-wise fMRI data analysis, typical task-related data set. So first, why do we have to take care of multiple comparisons? Suppose we have 100,000 voxels in the brain, right? So that's, the number of voxels depends on the voxel size, the resolution. But let's just assume we have 100,000 voxels. The typical approach is called a massively univariate approach, right? So that with 100,000 voxels, we build 100,000 models. So that means we have one model per voxel. With that approach, we have two assumptions. First, we pretend all those voxels are unrelated. There's no spatial relatedness among those voxels. When we build those models, we make that assumption. That's the first assumption.
In terms of the noise, you mean, because the signal can be related.
Yeah, the noise, of course. Yeah, you're right. So the second assumption is there's no similarity among those voxels. That's the second assumption. I'm going to elaborate a little bit more about the second assumption. So with those assumptions, we go ahead, we solve the model, typically general linear model. Then once we have the result, then we need to go through this ritual thing called multiple comparison correction. So with that correction, if this first assumption, the spatial independence holds, then we would have to adopt, for example, only correction. But that's not the case because those voxels are correlated to some extent, especially among those neighboring voxels. So that's why, in addition to correct for multiple comparisons, we have to take the consideration of the spatial relatedness, right? So that's where the different approaches come into play, right? So there are, for example, Monte Carlo simulations, random field theory, permutation test. So those are the typical approaches currently available in the field. But there are problems with that approach. Firstly, for people perform analysis, you realize that approach, typically the penalty is pretty heavy. That's because this assumption we assume all those voxels, they don't have common information that can be shared. So there's an information waste that directly relate to this heavy penalty. There are other issues I'm going to elaborate. That is tied up to the typical statistic protocol we call the null hypothesis significance testing, NHST. So with that approach, we start with a condition we call the null hypothesis. That's in the brain. We assume everywhere in the brain there's no effect. So that's basically, we have this straw man, right? So we pretend that nothing going on in the brain. With that presumption, then we find this surprise or weirdness measure. That's the so-called p-value. That p-value is a conditional probability. That is, under the condition, there's nothing going on in the brain, then what's the likelihood you would get the current data? So that measures the so-called p-value or the false positive. So with that p-value, there's this magic number of 0.05, simply because it's 1 out of 20. It sounds nice, right? So people adopt that threshold, use that magic number to make a decision. So that decision is pretty much similar to what's going on in the courtroom. We have this 2x2 matrix. So suppose we have this real truth, whether the person on trial is either innocent or it's guilty, or it's, in our case, it's whether we have nothing going on in the brain or there's something going on. So that's the real truth. Then we'll make a decision on this direction. So we have this 2x2 scenarios, right? So among this, the blue cells, that's perfect situation. But the problem is we have those two red cells. So especially this first one, this one. So nothing going on in the brain. Then we make a decision. We want make a mistake that we claim there is something going on in the brain. So that's the so-called false positive. That's the p-value. So when we do science, we tend to, when we have perform data analysis, we tend to control that probability. So that's why we care about the p-value. But there's another p-value, this cell on the lower right corner, that's called type 2 error. So there's something going on, but we fail to detect that. That's the second type 2 error, it's a false negative. But our focus is on the type 1. So with that approach, there are some issues. The first issue is the data we have is not like the courtroom. The courtroom is black or white, innocent or guilty. But the data we have, or when we talk about activation or whatever effect we talk about in the brain, it's not either you have activation or you don't have activation. So more likely, and there's strong evidence to show most of the brain regions are activated to some extent. So the point is not whether we have activation or we don't have activation. It's more practically whether our statistical evidence is strong or weak. So that's maybe more practical for us to identify. So that's one problem. We tend to artificially to dichotomize the evidence. So in the end, it's pretty much like a sea level, right? Above the water, we claim we have islands. Below the water, even though they're land mass, we just pretend they don't exist. So that's what typical the current situation. So the second issue is there's this two misconceptions. The first one is the p-value measures when we pretend that there's nothing going on, no effect, then measures the how surprised we are with the current data. That's the so-called p-value. That p-value is not the same with our data. The effect is zero. Those two probabilities are not the same. But for practitioners, for the person who analyzes data, they may tend to believe they are the same thing, but they are not. That's one misperception. The other misperception, if a brain region fails to survive whatever the statistical evidence after correction, people tend to believe that region is not activated. So that's basically you are saying, I don't have strong evidence, then that doesn't mean we have low evidence. It's not the same thing as there's low effect, but people tend to at least tend to make that mistake, has that vulnerability for that misconception. So the third issue is, in the field, this is not a secret. If your clusters fail to survive, then people tend to start to find a way to get around it. For example, okay, first maybe I can focus on the gray matter, right? So you reduce the number of voxels. Of course, that will be easier to survive. If that doesn't work, okay, then I say for my tasks, they're pretty focused on, for example, visual cortex. I can further reduce the data domain. So when you go through those different stages, your statistical evidence also becomes stronger and stronger. So the issue is your data is the same. You're not changing your original data, but as long as you change your focus, the statistical evidence is changing. Is that a valid approach? You can say, where's the borderline which you are doing p-hacking, for example, right? So that's something it's troubling. The next issue is whenever we publish a paper, the reviewers or the journals, they demand us to correct for multiple comparisons. You can only report those clusters that can survive, whatever the threshold. Then when people read the papers, you only say those survived clusters. We're bound to have the bias because of this thresholding, right? So that's, you can call that a type M error because of that filtering, you can call that a publication bias. You have this, you make this mistake, that's called a type M, inflated the magnitude. So I can go through a couple of other issues. The typical problem with neuroimaging data, people only report this statistic evidence. They don't report the real effect size, right? So you say they bring images, they show t value. The color bars, usually either there's a t statistic value or p value. Even t statistic, they don't even list the degrees of freedom, right? So you only say the effect size. Even in the tables, they put the coordinates and the t statistic value. Only t statistic only on the peak voxel. So people don't report the effect size. The next issue is this is more subtle, right? So the uncertainty is not available or not interpretable. Why? Why do I say that? You may say, okay, you have t statistic, right? But the issue is the reason we perform multiple comparisons correction, that means we don't trust those t statistic values, those p values. That's the reason we need to do correction. So if that's the case, we cannot directly interpret those individual t statistic values. So at the voxel level, even if people report the t statistics, those t statistic values are not directly interpretable because of multiple comparison issue. On the cluster level, you can either claim your cluster survives or fails to survive. There's no t statistic associated with that each cluster. So you cannot say anything about the uncertainty about your result. So either survive or not survive. That means it's either below 0.05 or above 0.5 at the cluster level. So that's another problem. I mean, that's for future, like when people do perform meta-analysis, for example. So the next issue is I call it a lack of spatial specificity. That's because you have a cluster survive. That cluster is just purely based on statistic evidence. Based on, for example, t statistic, you have that cluster colored with some, color spectrum. So that cluster may not be well aligned with your anatomic structure, may cover partially one anatomic structure, or maybe spill over across several anatomic structures, right? So people tend to use the so-called peak voxel to identify where that cluster is located. But that peak voxel you may miss if the cluster covers multiple regions. You may have difficulty to locate exactly what the anatomical regions are, right? So like this pretty common. If your statistic evidence is so strong that larger of the brain chunk regions are so-called activated, then how do you identify those regions, right? So that's the difficult. Lastly, because the current approaches, they basically use the so-called spatial smoothness or as a leverage to identify the survived clusters. So basically, if the region is intrinsically small, like amygdala, then you would have difficulty. Basically, you discriminate those small regions, even though those regions have roughly the same effect size, or even maybe stronger than the bigger regions. But simply because they are intrinsically small, then you are penalizing those regions. So those are some of the issues. So let's say if we can do something better. Look, start with the first toy example. Let's talk about NBA players. Suppose LeBron James during the current season is over, right? So his performance was 51%. That's his shooting percentage. Now let's say what he's going to do. His performance next season, right? We don't know. He has reached his peak, or maybe his performance will decreasing. We don't know. But without further information, I think we can reasonably say his next season, his performance is pretty much 51%. So if we don't have any further information, right? That's reasonable. Nobody, can argue otherwise. However, if I change the topic, let's make predictions for all the top 50 NBA players. Instead of just LeBron James, this one person, this one player. Then what are we going to do? Are we still adopt the same strategy using each player's current performance as a prediction for his next season? I can think of two approaches right now. One is called the low pooling. By low pooling, that means we just use the current performance as a prediction for the next season. That's called the low pooling. No information shared among those 50 players. Okay, low pooling. The other extreme, complete pooling, that means I'm going to use the average among those 50 players as a prediction for everybody. That's definitely not a good idea, right? Nobody does that, right? So those are the two extremes. So if I plot it out, the bottom is the current performance among those 50 players. The top one, this line, is presumably I can travel to the future next season, right? 1 year in the future, I can do time travel, then I find out those 50 players' performance. You can see some of them, I mean, this line, the prediction, if I adopt low pooling, I just use the current performance to predict their next season performance. So, I mean, we know some of players maybe will do better, some of them will worse. That's why you say those are purple lines, right? The slanted purple lines, not the vertical lines. So if we do that, we're going to make mistakes, of course. That mistakes is measured by the sum of squares, right? So that means this minus the current performance, that's error, then because some are positive, some are negative, so we need to do, that's why we need to sum of squares. So that's our measure our prediction error, right? So that's the proposed approach of, I call it a low pooling. So that's one possibility. Can we do a better job? Instead of a low pooling or complete pooling, basically we use the average amount. That's probably would be a 47, 48%. Okay, can we do a better job than this? Surprisingly, actually, there is a better approach. That approach is we do partial pooling. What does it mean, partial pooling? We're going to basically, so this is the bottom, again, that's the same as the previous slide. That's the current performance. The top line is also the 1 year later, that's a future. We're going to use the future as our y. This will be x. We just do a regression. Our regression model, y equals a plus bx. That's a simple model, linear regression. If we do that, then we're going to predict that result would be, we call it partial pooling because we know the phrase regression to the mean, right? So we tend to pool those high performers and the low performers to the middle. So that's regression to mean. That's why we call it a partial pooling. So with that approach, you notice that we still make mistakes, right? Those mistakes is bit smaller than the previous slide. Previous slide, you can see here, that's the sum of squares. This is smaller. So the point here is we care about the overall prediction error, not each individual player. If each individual players, of course, this is, if we focus on one player, for example, LeBron James, our prediction may not be optimal, but our focus is the overall prediction error. So from that perspective, the partial pooling is a good strategy. So that is basically, in this context, it's basically the regression model. So it boils down basically our assumption. On the previous slide, we assume all those 50 players, they have nothing common. There's no information we can share among them. So that's why our prediction is just use each individual player's current performance to predict the future. Equivalently, that's basically we're saying that those 50 players follow uniform distribution, no information shared. Okay. Here, with partial pooling, we're doing regression analysis. We make our assumption those 50 players follow Gaussian distribution. That's like we do. We recruit subjects for fMRI study. The typical model, of course, we don't mention it, but that's our underlying assumption. Those subjects, in this case, those 50 players follow Gaussian distribution. That's basically if we call that prior, that's our prior information. So that's why we pull the information, partially pull, we drag them to the center. So that's this partial pooling approach. Now you may ask, because previously I mentioned one issue about the current correction for multiple comparison is if you change the data to some extent, you limit the whole brain to the gray matter or to visual cortex, you're going to change your p-value. You're going to change the evidence, even though the data is the same. You just restrict the region. But suppose I want to, first I want to mention that this with 50 players, this is Y, right? That's the next season performance. The X is the current performance. So what we are doing with partial pooling is this green line. That's the regression to the mean. You can see the impact. The dotted line, that's a diagonal. That's the low pooling, right? So that's basically using the current performance to make a prediction for the next season. So that's basically the impact of this partial pooling. So we drag them to the center. So that's 50 players. Now the question is, if I expand those 50 players to the top 100 players, would that change my prediction? So I raise this question because for neuroimaging, if we change our data, our focus on visual cortex, you are going to change the p-value after correction, right? So would I still suffer that problem? So this is this plot basically shows I keep those top 50 players, those are the circles, the same as on the left plot. Those cross signs are the next 50 players. So with those top 100 players, I make another prediction, which is this blue line. So the dashed green line is the same green line on the left-hand side because that's the line for the top 50 players. Yes, I will make a slightly different predictions, but the difference between the two is pretty negligible. So even though I changed my data from 100 players to the top, from 50 players to 100 players, the prediction is roughly the same. So that's something, maybe it's a nice property we can, later on we can leverage. So that's the first toy example. The second toy example, let's look at the kidney cancer death among those counties in the US, okay, those continental 48 states. So on the map, this shows this is the real data from during the decade in the 1980s. So during those 10 years, here shows the highest number of deaths among those 3,000 counties in the US. So you may notice those counties are pretty much in those less populated regions, right? So it's not, usually they're not in the metropolitan area. Then why is that? Why those rural areas tend to have really high kidney cancer death, right? So first time when people saw this, they came up, well, this is a surprising map, right? So they came up with a few hypotheses. Maybe because of their access to healthcare system is not as good as big cities, or because of radiation, or some other reasons. You can come up with many reasons. So basically, this needs further investigation, right? Why those counties tend to have really extremely high kidney cancer death, right? But that's just one map. There's another map that shows the counties with the lowest kidney cancer death. Surprisingly, those counties also tend to be less populated, also in the rural area. But now the big question is how do we reconcile the two maps? Okay, so that's the challenge we face. Well, maybe those hypotheses may be reasonable to some extent, but the real problem from statistical perspective is because the fact that kidney cancer is a rare disease. It's so rare Let's use a simple example. Suppose the death rate, kidney cancer death rate is 1%, 1 out of 100. This is not a real number, but let's use that as an example. 1 out of 100. Suppose a group of people, only 50, you may have 0 death, right, in that case. Or you may have 1 by chance, or 2. If you happen to, among those 50 people, if the death rate is 1%, 50 people, you have 1, even have 1 death, that person will end up, that county would end up on the left-hand side. Right? If you have 0, you end up on the right-hand side. So basically, it's a sampling issue. When you have the occurrence rate is low, then you end up the situations like this. But I'm using this example to maybe can teach us something about the brain imaging situation. Why? Because we have 3,000 counties. Each county we want to make some decision whether to estimate the kidney cancer death rate. Well, this is the survey data. Is a way we can give us a better sense. In addition, instead of fully trust the original data. So that's the point. Maybe we can do something calibration or the partial pooling approach. So, or you may argue we can borrow the idea from neuroimaging. Why? Because we have over 3,000 counties. Maybe we consider as a multiple comparison issue, right? We need to somehow correct for that fact. How? Divided by 3,000? Conformity conversion, maybe that's not reasonable because you can argue the neighboring counties are related, geographically related, maybe they share some relatedness, right? So but actually it's the other way around. Maybe we can borrow the idea from this example and apply to the neuroimaging situation. Why? Because we don't really care about whether it's the so-called null hypothesis. We don't need to attack that straw man, right? It's not whether there's a 0 kidney cancer death. We don't care about that. We more care about the 2 different types of errors. One is called types S. You make a mistake about the sign. For example, 2 counties. On the previous slide, I showed the left-hand side, you have the highest death rate. The second, on the right-hand side, I show the lowest death rate. If 2 counties, does that tell us we should move from one county A with the highest rate to the right-hand side of another county? So that's, I call the type S error, right? So that maybe we need to take care of that. The second mistake is that we maybe tend to overestimate or underestimate the kidney cancer deaths. So those 2 types of errors, we tend to care more instead of a so-called p-value, the false positive or false negative. So we're changing our focus. So that's by changing that focus, then we don't need to do multiple comparison. What we can do? How do we can do better? Well, we know all those counties in the U.S. we share something common. That common, we can build one model instead of treating each county as an isolated entity. So we can do some information sharing, build one model. With that one model, we focus on a research hypothesis instead of a so-called null hypothesis. That research hypothesis, with my data, what the kidney cancer rate is, greater than, 0.00 or 0.021, whatever the number, we can get a probability, right? Get that with that we call a posterior probability instead of the so-called p-value. So that's the message we can borrow from that kidney cancer case. So with that, now we can do something different. That basically from those 2 examples, basically we get rid of the prior information. We pretend those voxels or those NBA players or those 3,000 counties, the uniform distribution may not be a good idea. Instead, we adopt a different approach, adopt this using this Gaussian distribution for those subjects, for NPA players, for counties, and for brain regions. Maybe we can do that too. We have been doing that for the subjects we recruited, right, for the study. We can do the same thing for the brain region. So with that, we can build one model. Then we can control the two different types of errors, type sign and type magnitude. So let's summarize what we have learned from the two examples. So we basically abandon the null hypothesis approach. We don't calculate the so-called p-value, right? So that's we pretend the p-value is we pretend there's no effect. How surprised we are with the data. So that's the traditional p-value. Instead, we focus on with my data, what's the effect or the activation. So we change our focus. Then we build one model instead of 100,000 models. So with one model, automatically, we don't have the multiple comparison issue, right? So with that, basically we adopt the partial pooling approach. Then there's a few other advantages, like for example, we port the whole full results. We don't have to dichotomize our results. You can highlight some of the data that shows strong evidence, but that does not necessarily mean you have to hide the rest of the results. So those are the advantages. But let's use a real example to demonstrate how we practically apply this approach. So this is a real data set. We have 124 subjects. So at the individual sublevel, we have this some effect. In this case, it's a set-based correlation. I mean, it could be a task-related experiment. But anyway, so with 124 subjects, we'll end up with 124 beta values per voxel, right? So that's the data we have. When you go to group level, our model is basically we have a behavior data as an experimental predictor, as an experimental variable. So basically at the group level, the traditional approach, you have y equals a plus bx plus the residual. So that's the model. So with 100,000 voxels, we build the traditional approach, we would build 100,000 models. So y equals a plus bx plus epsilon. So that's the so-called massively univariate approach, right? So with that approach, this is called the general linear model, right? So basically it's a simple regression. With that approach, I mean, I already mentioned that we assume all those 100,000 voxels are on. We pretend there's no information we can share, and during the modeling approach, even though the neighboring voxels are correlated for the residuals, are correlated, but right now, during the modeling approach, we ignore that effect, right? So that's why we saw those 100,000 models separately. So with that approach, in this particular study, we care about the slope effect. Basically, how is the brain response? In this case, the set-based correlation is related to the behavior. So that's this B. So that's the model we have. So if we do the whole brain voxel-wise analysis, then we go through the second step, right? That's the correction for multiple comparisons. So you can use several ways. I mean, here we simply just use Monte Carlo simulations. With that, the current standard, I mean, typically the reviewers will ask you to use the voxel-wise p-value of 0.01, for example. That's because a couple of years ago there's a paper that shows that you need to be stringent at the voxel p-value to be able to get the cluster to achieve more reliable corrected p-value. So if we adopt that criteria in this particular data set, only two regions, two clusters managed to survive. So those are the two. If you loosen the criteria, right? So most of you are probably not agree, but you may get 4 clusters. But that's as much you can do about this data set. So can we do something different? So suppose instead of focus on the voxels, we focus on 21 RIs. Okay, we're not doing box-wise analysis. Let's just focus on RIs to demo their modeling approach. Those 21 RIs were picked based on the literature, not based on the current study. Okay, so from the literature that relate to the behavior theory of mind in this context. So with those 21 RIs, the traditional approach, you would still build 21 models. Okay, so with that approach, in the end, we still have to take care of the multiple comparison issue, right? So what you can do, divide by 21, your p-value, that's the typical buffer-only correction, right? So that's probably not a good idea. That's why the RI approach usually is not adopted and failed because of this severe penalty. Right? In the whole brain, you could leverage based on the spatial relatedness, but at the RI level, 21 RIs, no, I mean, we don't have that leverage, spatial leverage. So let's do something different. Basically, we build one model, right? So previous slide I showed with 21 RIs, you have 21 models. We build one model. That's why here I have 2 indices, right? With this model, the first part, A plus BX, is exactly the same as the previous slide, right? But there's a difference because I don't have index for the intercept and the slope. That's because that part is shared by all the subjects and by all the brain regions. Yeah, the I is the subject, the J is the RIs. So that's why the behavior here, you have the index xi. So that's a behavior for each subject. So this part is shared by all the regions and by all the subjects. So the next part, that's new from the traditional approach. Traditional approach, you just have A plus BX plus the residual, right? Here I have something that is extra. So let's focus on the red box. The red box is new from the traditional approach, right? Why it's new? Because since we merge all the regions into one model, so this part, index I, remember that's the subject, right? So that basically captures each subject has. I have the common one, right? The A plus BX, basically it's shared by all the subjects and all the regions. I need to account for quasi-subject variability. That's why I have that pi sub I, because each subject has something uniqueness. So that captures the subject quasi-subject variability. This part is indexed by J. That means each region has their unique contribution related to the common one, A plus BX. So the data, I partition the data into those 3 components. First, I have the common one shared by all the regions and the subjects. That's in the traditional studies, so this is called a fixed effect. Then I have the second component is the red box. That's people call it random effects because they fluctuate. They fluctuate relative to the fixed effects. The last component is the residual. So I break into 3 components. Yes, Bob.
I'd like to point out that the distinction between this and the previous model is that the idiosyncratic effects of ROI, the J's, and of the subjects, which were fixed effects of the previous model, so they're estimated for every single subject separately, every single region separately, that instead it's all pooled in, they're just assume the random numbers, we're not going to try and estimate them separately, we're just going to estimate their standard deviations or their variances. So this reduces the amount of estimation, makes it a more complicated math problem, but it's simpler in the number of free parameters, which is which is this constraint of the regions being together, though there's no correlation necessarily involved. It's just this turning the fixed effects, part of the fixed effects into random effects reduces the amount of freedom, which we had too much freedom for.
Do you rely on Gaussianity? Or could they have a different distribution?
Then the problem becomes, in principle you could do that, but the problem becomes much harder to calculate. Well, those distributions of the pies and stuff could be non-Gaussian, but then you run into the problem of estimating the parameters of those.
So it's nice if they're Gaussian.
Life is a lot simpler.
Yeah. So here I have, you call it a prior distribution assumption. So cross subjects, we have the Gaussian distribution assumption. Cross RIs, we also have this Gaussian distribution assumption. We can argue whether that's a good idea or not. We can delay the discussion about that. But basically, with that assumption, practically, we can easily solve the system. That's called the linear mixed effects model. But the problem is, when we solve this system, we get the estimate about A and B, right? But we don't get those individual random effects. We only get the variances. The variances for cross-subject variability, variances for cross-region variability, right? So we estimate A and B, but we cannot say anything about those individual subjects. We cannot say anything about each individual RIs. Remember, J is for regions. So for us, this is what we care about. They shared by all the so-called fixed effects shared by all the regions and our subject. What we really want is A plus this for each region. That's a unique part. That's the intercept. For the slope, we want that plus each RI's unique contribution. So that's what we really care about. But under this linear mixed effects form, we can't get what we want. That's the problem, right? So even though this model is nice, because we have this just one model, we don't need to worry about the multiple comparison, but the problem is we can't get what we want. So that's sort of we have the problem. But how do we get rid of the problem? Is we basically get out of the traditional statistical paradigm. We jump into Bayesian framework. How? Well, the model is exactly the same.
So a question about the model. This model is less flexible than the previous one, right? Because these betas is only region dependent. So there is no variation between these regions anymore.
Well, there is. The region it varies. Yeah, the region, varies. I just assume the regions follow Gaussian distribution. I'm not saying how exact the variance is. The variance will be estimated based on the data.
Well, but he makes a good point. The previous model, not the fixed effects model, has a lot of flexibility, right? The variance in each, the mean and variance between all the regions are completely separate. And the linear mixed effects model is moved a lot of that into random parts, which means that you can only estimate the variance and you can't estimate anything about the individual regions. What he wants is something in between those two.
Yeah, right.
Because in one, you've got fewer parameters to estimate. They're constrained to all the models for the idiosyncratic effects are subsumed into a single distribution, but as opposed to 21 individual distributions, you want something where it's somewhere in between. That's so that you can get individual estimates, but they're not blowing in the wind of a hurricane, flapping all over the place. Although that really makes sense.
Thanks for the explanation, Bob. They are basically, so with this assumption, right? So we can, on the previous slide, the linear mixed effect model, we can only solve the variances. We cannot get those individual estimates, especially, particularly for us, we care about the each RI, right? So we want to achieve the goal of getting this. How do we get out of that problem? Is basically, we don't treat those two parameters in this case, A, B. Previous slide, we consider them fixed. Fixed pretty much like the physics concept of like speed of light or a gravitational constant. They're fixed. But here, practically, we don't consider them fixed. We consider them as random variables. We attach them with a distribution. So once we are willing to do that, then we are stepping into the territory of Bayesian modeling approach. With that approach, well, as long as we're willing to treat all the parameters as random variables, then we can get the distribution of all the for all the parameters. Then we can get the distribution for them. In this particular case, we care about that. We can get the posterior distribution. So the technical approach is in this framework. We can use the numerical scheme of Markov chain Monte Carlo simulations, the famous acronym MCMC. So with that, then we solve the problem, right? So how? Well, how exactly the result would look like? Remember, in this case, we have 21 RIs. So with 21 RIs, we solve that model. So in the end, no more p-value. For each RI, we have this distribution. With this distribution, then we can say something about each region. For example, the first region, for all the plots, the vertical bar is shows the zero effect. So for the first region, basically 99% of the mass, the density is above zero. So I think everybody agrees with me. We can comfortably claim this region will have strong evidence, right?
That's your B plus beta J distribution.
No, this is for the B, the slope.
Just B.
Just B, because that's what in this particular study, the investigator is interested in the slope effect.
There really is no beta J anymore. BJ
Yeah.
anymore. It's just B, but B is a random effect with non-zero mean. So in a sense, it's B plus BJ.
Yeah, it's B plus beta J. Yeah, in this case. Yeah.
But they're estimated together now.
Right. Well, no. Each parameter does have a distribution, so I can assemble it. Yeah.
Wait, sorry, is this B plus beta J?
Yes, it is.
Wait, that was my initial question. I got the letters mixed up. That was my initial question.
Okay. Yeah. Yes, it is. So the J from 1 to all the way to 21. So for us, this region, I mean, it's not ambiguous, so we can make a strong statement. For this region, it's the zero is here. Can we say something about this region? Well, if you calculate the density above zero, it's about 94%. Do we have to adopt the so-called 0.05, the magic number, as a threshold? I don't think so. So in this case, yes, I mean, I can report all the 21 regions, the results, full results like this. I can also highlight some of the regions, which, I mean, I can say, you can still based on peak of 0.05% density, but that doesn't necessarily mean I can't say something about this region, even though it's only 94%, the mass is greater than zero, right? We don't have to use the hard thresholding, right? So the point here is we can report the full results. With that, in the future, if another study happen to have this region result, maybe you can still use this as evidence, right? So no more hard thresholding. You can highlight some of the results. That doesn't mean we don't have to hide the rest. So that's one big advantage. Another thing I want to notice is that, remember at the beginning I say only 2 regions managed to survive the current whole brain voxelwise analysis. So with this, I think at least I can discuss 9 regions. Plus, even this region, it's not just Canadian, I mean, doesn't pass the so-called 0.05 threshold. That doesn't mean I cannot say anything. If happens in the literature, previous publications maybe already discussed that, or even not, I can still say something. You have some moderate amount of evidence to show the effect for that particular region. So that's something I think I consider nice. And this is not a p-value. I want to also emphasize that because the p-value is specifically defined as you pretend nothing going on. There's a null hypothesis associated with the p-value. So that's why this is, when I talk about p-value, we're talking about the probability. Probability with my data, what's the effect is greater than 0. That's the probability we're talking about here.
But, so I don't understand really what those curves are. Are those simulations of?
Yeah, you can say it's simulations, but it's based on the model.
Okay.
It's you can call it Markov chain Monte Carlo simulations. Yes.
Yeah. And then, so what are the b-values then eventually? So eventually you want to report b-values, right?
The p-value?
The slope, no, the slope.
Oh, the slope, yeah. So the slope is it's distributed among the curve, but
you,
yeah,
if you would report one value,
you could. You can report the mean, for example, or median,
yeah, okay.
or mode.
Yeah.
There are several ways. This you can plot this bar graph, or you can put in a table. I didn't put it a table in the slide, but you can report a table with mean, with standard deviation, with the probability too. So this is just different ways. The previous slide I just want to show the fault distribution. So that's a second way. Yes.
Does this approach potentially sort of ambiguate two different situations where, let's say, the B that you're estimating stands for some physical quantity, whatever,
right,
subject's anxiety level or something
right,
like that.
Mm-hmm.
Now, if I estimate a distribution for the B, does that mean that this quantity varies across time amongst sub? Does it just simply mean that it cannot be estimated?
No, it simply means, well,
accurately?
first I want to start with, there's uncertainty about everything in life except death and taxation, right? So that with the data, we also have uncertainty too. The current approach, they give you the beta, but that doesn't mean that beta is exact. We also have uncertainty. The uncertainty is standard deviation. It's embedded in the t statistic.
Well, I think I was asking, suppose you had 121 subjects. Suppose now you get 1,000 more subjects. Will those things collapse into much narrower distributions, or will they not? And the answer is probably some of you both.
Doesn't that depend on what's measurement
Yes.
error and what's
Yes,
the underlying?
Inter-subject.
Yeah.
I think
I guess that's what I wanted to
that
know.
gets
Does
into-
that reflect something about that's different between the 100 subjects, or does it?
This gets into
reflect
the types of
measurement?
uncertainty,
Yes,
and I
I think
think
it's
it goes
gonna be
back to
both.
the aleatoric epistemic.
Yeah, it would be similar to the traditional approach because this boils down to our symptoticity. Or the central limit theory. You have more sample size, of course, you can do.
If you have the speed of light as one of your variables, your distribution should shrink as you add more and more. But if you have, there are other kinds of things where it'll asymptote to a distribution that reflects the population's inherent variability, right?
The question is there a way of telling the two apart?
If you get more data, it's just for a given, I would imagine if you have a larger and larger sample, how it changes, that's how you would see it.
It depends on the samples, the subjects. Do you have more? If you have 1,000 subjects, we tend to have more heterogeneity across subjects.
Well, you can imagine in your case, suppose
Uh-huh.
that there are certainly in your population, it turns out that there are some people for who the true B slope is 0. That there's no it doesn't care about the theory of mind, mindositiness in the people that are left-handed or something. But, and then in other people it does. So then your thing
Yeah,
not
right.
collapse to a single
Right.
point, right?
Right, yeah. Yeah, like they probably didn't include, for example, autistic kids, in this study. So if you expand this number of subjects, you may include something which you didn't think of, some subjects. Then that may not be exactly or symptotically converge to the ideal situation. So this is basically separate second way to summarize the result. Also, one thing I want to mention is that here, each region I show two results. The left one is the traditional approach. So I analyze that region independently. This one on the right-hand side, that's the Bayesian approach. You may notice there's one phenomenon is that they tend to be dragged to the center. That's a partial pooling effect, right? Notice this black bar, that's the mean. So this traditional approach tend to be higher, right? Of course, there are a couple of exceptions. For example, this one is the opposite, but that is the partial pooling impact, right? So they shrink to the center. So that's pooling because the two extreme. One extreme is basically I just trust each region's own effect. That's the traditional approach. The other extreme is all those 21 RIs, the average. So those are the two extremes. But what I'm doing here with the Bayesian approach, I do partial pooling, depends on which force is stronger, is going to pull to the center. Center somewhere, that depends on the counterbalance between the two extremes. So it's weighted average between each individual RI and the overall average. So that's why you see this pooling effect, right? So that's also other way to describe is I tend to be conservative about the effect. That's why I downgrade the original estimate for most regions. So even though I don't have multiple comparison issue anymore, but I have a different perspective. I tend to be conservative about the effect. So they are largely smaller than the original, the traditional approach. So that's why this would help us to control the type M, the so-called type M magnitude problem, right? So I tend to be not fully trust the original result. That will help us to control the type S and type M error. So that's the modeling results. Now you may argue, how good is your model? The traditional approach, you have your result, you just write your paper. You don't talk about how good or how bad your model is. But with the Bayesian approach, then we have different ways to judge each model. Okay, so we can visually check. There are a couple of other ways, but this visual check is nice. The black curve is the original data. So those two plots, we have the same black curve. That's the original data. Okay, we share the same data. The traditional approach, general linear model, in this case, a simple regression. We have the model. With the model, I can use the model to generate more and more data, just do simulations. Okay, you put different variables. I just randomly draw from the model. That's this blue cloud is. So with the traditional approach, I have this blue cloud. With the Bayesian model, I also have the blue cloud. I think you would agree with me, the Bayesian model is not perfect, right? But compared to the traditional approach, I think it's a little bit better, right? So that's we call it prediction error. That's similar to the case of the NBA players. Either we use each individual players to make a prediction for the next season, or we use the regression to the mean, the regression model. Same thing, same concept here. So that's called a prediction error. I mean, that's called a posterior predictive checking. So we can visually check how good your model is. There are a couple of other ways, for example, using leave-one-out information criteria or the other couple of other approaches. So that's we can validate your model. Of course, there's always room to improve it in the future, right? So that's one data set. We can apply that to several other scenarios. Here, I'm just want to show one example is in neuroimaging, people do so-called, for example, functional connectivity, right? So you have some regions. In this case, I don't remember, 16 regions. With those 16 regions, you calculate correlation values for each subject. Then you go to group level, you can see how those regions, their correlation values at the group level. The traditional approach is pretty much similar to the massively univariate approach. You analyze each element, each correlation value separately in that matrix, right? So that's at group level. So that's a traditional approach, general linear model. With the Bayesian approach, I build one model. So I end up with this. The traditional approach, once you are done, you're not done yet. You have to take care of the multiple comparison issue. in this particular data set, none of them can survive the multiple comparison correction. Even though I highlight color those cells, but once you apply multiple comparison correction, none of them can survive. But with the Bayesian approach, we don't have the multiple comparison issue. So in this case, since it performs, I don't know, called beta or not, but at least you can also visually check the model performance between the two models. Okay. So
I think it depends a little bit then on the question whether you have to do this multiple comparison analysis. So if you ask, or if your question is like, what are the elements of the correlation matrix, and I want to be sure that all of them, there is none of them incorrect with a p of 0.05. I mean, then you can do that, but then nothing survives. But you can also say, well, I just want to see the pattern of the correlation matrix. And at the p of 0.05, it's 95% accurate, this pattern. And I don't do any multiple comparisons correction. I just use p of 0.05, and this gives me the pattern. And then you can compare this pattern with other subjects or tasks or whatever. Right, so I don't just the question or the requirement that this matrix has to be correct for every single element at the 0.05. I think it's kind of a silly question. Well, in general, we don't do that with neuroimaging either. We don't ask whether every single pixel is correct. We just say, or often we just want to see the pattern of activation, and if that pattern is correct by 95% chance. Then,
but that
is a reasonable measure, right?
But the pattern, I mean, when the 0.05 is at each individual voxel, each cell.
Yeah, right.
But collectively, you still, if you don't correct for multiple comparison, the overall false positive rate will jump way above 0.05. That's the problem.
Then the chance that your matrix is not 100% correct is pretty big.
Yes, it is.
But in general, you just look at the pattern of the correlation matrix. You're not going to compare whether one cell in that matrix is different between one group versus the other.
But then I can't argue the pattern maybe is just pure noise. Since you could make if you cannot survive the correction, that means you have a chance.
Noise, it will not have any structure, right?
Yeah, I know, but
it'll be, I mean, there's different ways to do that. But if you see with one group this pattern and you see a similar pattern,
right. So on the right hand side, I would avoid this false positive rate. So I don't have to worry about this to convince reviewers or anybody about this. So basically, in this case, I just present the whole picture. I don't have to do thresholding. Simply, I highlighted some of them. That's because I want to highlight it. You
could also show the whole pattern on the left, right? You just don't threshold it. You
right.
show the pure.
But you look at the current publications, you do say people hide. They only show those survived cells.
Yeah,
even in the hallway, in the building 10, you walk through the hallway, you can see those are circuit plots, those are graph, so-called graph theory. They just show those survived the path, they call the path.
Right.
That's what they do. They don't show the whole thing.
Right. But then it's really important which cells are there and which are not.
Right.
Which you don't really have a good way of saying, right?
No, you don't. I mean, we're talking about the correlation values here anyway to start with. So this.
I'm asking this because we, as you know, we have this publication. We just want to show a pattern of it. And then the reviewer wants us to do multiple comparisons correction. And if you do that, then it won't show anything. Because you need a correlation of 0.35 or so to go over the threshold for 100,000 pixels and 100 degrees of freedom.
Yeah, I know, but that's the current thing. I mean, it's difficult to.
I think that's a rarity. I mean, most people they make a table of clusters and they say these are our significant clusters.
But why do you need clusters? So I don't.
But that's what most people do.
Yeah.
They don't have to, but most people don't say, here's my whole brain set of beta values, and then someone else can do it, correlate the whole 3D volume with those people. That isn't what people tend to do.
Yeah, so
I
it's
think
sort of
what
it is
people-
accepted to clusters, but it's as arbitrary.
No,
as
no,
it's
no,
shown
but there's,
over.
I mean, there's good reason. Well, for one, in many studies, people are interested in clusters. Like most
Well,
people
they
want
wanna reduce-
specific regions
Well, they want to
can
reduce the
hang
data.
their
It's a
hat
dimensionality
on.
reduction.
But the other reason is that the clusters are a way of evading very restrictive single voxel statistical thresholds. So,
But then you may
basically-
lose the LGN. So we
Yeah,
So this is about, I guess
So
this is the way.
it's always a trade-off.
No, not if you show the whole thing. If you don't show,
But most people want to reduce the dimensionality of their data. So that is, but your approach is a different, you're avoiding this problem in a different way. Sure.
yeah.
But most people don't.
But
They
what
make a
all I'm
difference.
saying is, I wish that was more accepted by the reviewers to show the whole thing.
Well, I think some people are trying to make, that's why people want to like register your data and you upload your whole beta and, well, you upload your T-stat map to somewhere and then someone else can pull it down and look at it.
Yeah, that's eventually the best thing.
That is more in line with what you're.
Yeah.
And that's a better way to compare things, sure.
Yeah, I'm pretty much done. I think that's basically summary. If I have one slide that demonstrates the approach I'm promoting is basically this kidney cancer maps, those two maps. All right, that's all I have.